Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If we launched our fastest, absolutely most advanced chemical rocket today, and we aimed it straight at the nearest star system,
Alpha Centauri.
Right, Alpha Centauri, it wouldn't actually arrive for another 70,000 years.
Which is just an incomprehensible amount of time for a human mind.
Exactly. It's essentially an eternity.
Yeah.
So if we want to actually survive the cosmos or, even just explore our immediate stellar neighborhood within a single human lifespan, we have to completely stop relying on controlled explosions.
We really do. Chemical rockets are a dead end for interstellar travel.
Yeah, and that means we have to fundamentally rethink how mass moves through a vacuum, which invariably forces us to look at beamed energy propulsion.
Specifically, laser-driven light sails.
Right. But pushing a macro-scale object to relativistic speeds with photons, it isn't just a matter of building a bigger laser.
No, not at all. It's so much more complicated than that.
Because the universe actually has built-in aerodynamic limits, even in a complete vacuum. So we are going to explore the granular, the quantum-level mechanics of photon momentum.
And a really fascinating newly mapped threshold.
Yeah, this newly mapped threshold at exactly 75% of the speed of light, where the fundamental laws of relativistic physics they mutate.
They absolutely do. They turn our own propulsion systems into an active drag force.
Which is wild. But before we get to that wall, we should probably talk about why we're abandoning rockets in the first place.
Right. Well, the whole problem with chemical propulsion is rooted in the Tsiolkovsky rocket equation. It's basically an exponential trap.
An exponential trap, yeah.
Yeah.
Because you have to carry the fuel.
Exactly. You carry mass to produce thrust, right? But then you need more thrust to move that extra mass you're carrying.
It's like packing for a road trip, but the extra suitcases require you to tow a full other car just to carry the gas for the extra suitcases.
That's a great way to put it. And when you run the numbers, to reach even 10% of the speed of light using conventional chemical propellants, the mass of the fuel required would actually exceed the mass of the observable universe.
Wait, literally the entire universe?
Literally. The math just completely breaks down. It's physically impossible.
Wow.
And even if we scale up to, say, theoretical fusion drives or, antimatter engines.
Which we don't even have yet.
Right. But even if we did, you are still carrying the fuel. You are still suffering that logarithmic penalty of pushing the mass of the thing that's supposed to be pushing you.
So we're just stuck in that trap.
Exactly. So the only physical loophole we have left, really, is decoupling the engine from the spacecraft entirely.
Decoupling it. So you leave the engine behind?
Yes. You leave the heavy propulsion source, the massive power plant, and the energy emitter anchored safely in our solar system, and you just transmit the momentum across the void.
Which brings us to radiation pressure. And I think the concept of the solar sail is, it's generally pretty well understood by most people.
Yeah, it's a popular sci-fi concept.
Right. This idea of a massive, ultra-thin sheet catching sunlight, sort of like a galleon catching the trade winds on the ocean.
It's a beautiful image, but sunlight disperses way too quickly.
Because of the inverse square law, right?
Precisely. The inverse square law dictates that by the time a solar sail reaches, say, Jupiter, the sun's actual pushing force is just a tiny, tiny fraction of what it was when it was at Earth.
It's basically useless for getting to another star.
Completely. For true interstellar transit, you can't just rely on ambient sunlight. You need a highly collimated beam.
Like a laser.
Like a massive array of lasers.
Yeah.
A phased array, perhaps spanning, hundreds of kilometers across the lunar surface.
Just firing a tightly focused beam of terawatt-class continuous light directly at a sail.
Exactly. And the spacecraft itself carries zero fuel. None at all.
It's entirely just payload and a reflective surface.
Right. And the physics of this relies on the fact that while photons possess zero rest mass, they do actually carry momentum.
Which always trips people up. No mass, but they have momentum.
It's counterintuitive, I know. But their momentum is dictated by their energy divided by the speed of light. So when a photon interacts with the atomic lattice of a reflective sail, it actually transfers that momentum.
Because it's a physical push.
Yes. It is an infinitesimally small kick, of course. But in the near-perfect vacuum of deep space, devoid of any real aerodynamic friction.
You can just accumulate that acceleration continuously.
Exactly. If you maintain that multi-terawatt laser focus for days or months or even years, the acceleration compounds. The sail goes from a total standstill to a significant fraction of light speed.
But the actual mechanical interaction there, like the exact moment the photon strikes the sail material, is far more complex than just a simple elastic collision, isn't it?
Well, massively more complex. It's not just a billiard ball hitting another billiard ball. Physicists Chao Shen and Jazzy Li at the Harbin Institute of Technology recently deconstructed this whole interaction.
Right.
And they broke the thrust down into 3 distinct, measurable forces that are actually all occurring simultaneously.
Yeah, looking at Shen and Li's breakdown of this, I was really struck by how they split up those thrust vectors. Because, you start with just the baseline force, right? The incident light.
Right, the raw arrival of the photon.
Yeah. The photon arrives from the laser array, it strikes the atoms of the sail material, and it just transfers its initial forward momentum, like a kinetic slap.
It's the most straightforward part of the physics, the wave packet just hitting the surface.
But the real efficiency, the thing that actually acts as a multiplier effect, comes from the second force, which is specular reflection.
That's the golden ticket right there, specular reflection.
Because if the material acts as a perfect mirror, momentum conservation demands that when the photon completely reverses its direction when it bounces off, it imparts a secondary equal kick of momentum to the sail.
Yes, you are essentially double dipping.
Which is great.
It's ideal. Specular reflection is exactly what you want because all of the momentum from that clean, 180-degree bounce is directed perfectly backward toward the emission source.
Meaning 100% of the reaction force pushes the sail perfectly forward.
Right along your target vector. And if we could engineer a mathematically perfect mirror, the calculations for interstellar travel would be incredibly straightforward.
But we can't.
No. Real materials introduce the third force, and this is where all the complications begin. And that force is diffuse scattering.
Right. Diffuse scattering. Because no macroscopic material is actually perfectly smooth.
Or perfectly reflective at the atomic level.
Right.
A certain percentage of the incoming photons just won't bounce cleanly.
What happens to them instead?
They are absorbed by the material's atoms. This briefly elevates the electrons to a higher energy state for just a microscopic fraction of a second.
And then
the atom drops back to its ground state, and it has to re-emit a photon.
Right. And because of the nature of spontaneous emission, that re-emitted photon doesn't actually remember where it came from.
It has no memory of the laser beam.
It just gets shot out in a completely random direction across the rear hemisphere of the sail.
Exactly. And this is inherently inefficient because you are introducing vector cancellation.
Vector cancellation. So if a photon is randomly re-emitted, say, sharply to the left.
the reaction force kicks the sail to the right.
Right. But then, statistically, another photon is being scattered to the right.
Which kicks the sail back to the left.
So all that lateral momentum is just completely canceling itself out.
Yes, it's generating heat, it's causing internal stress on the sail material, but it is contributing absolutely zero net forward thrust.
You're just bleeding potential energy into chaotic, multi-directional noise.
You really are. You lose a massive percentage of your pushing power to that geometric inefficiency alone.
That seems like a huge problem.
Well, under normal Newtonian mechanics, at low speeds, this diffuse scattering is simply modeled as a constant fractional loss. It's an annoyance, but manageable.
You just calculate it and move on.
Exactly. You calculate the ratio of specular reflection to diffuse scattering based on whatever material you're using. You subtract the wasted lateral vectors, and boom, you have your baseline acceleration curve.
So you just build a slightly more powerful laser to compensate for the inefficiency.
Right. You just brute force it with more gigawatts. But, and this is the crux of Shen and Li's model, it doesn't stop at low speeds.
Because the whole point of a light sail is to go incredibly fast.
Yes. The goal is to achieve relativistic velocity. And as you push past roughly 10 or 20% of the speed of light, classical mechanics completely break down.
And the weirdness starts.
The weirdness starts. Relativistic effects begin to heavily distort the incoming laser beam.
Right. So we immediately run into the relativistic Doppler effect.
Yes.
Now, I think everyone understands standard Doppler shifts, like a siren passing by, so we can probably skip the acoustic analogies here.
Fair enough.
The real issue here is severe redshift from the sail's frame of reference.
Very severe. As the sail accelerates to, say, 0.12c or zero point 0.3c, it is literally running away from the incoming electromagnetic waves.
So from the perspective of the sail itself, the wavelength of the laser light is just being violently stretched out.
It is, the frequency drops. And because a photon's energy is directly proportional to its frequency.
Planck's constant times frequency, right?
Exactly. Because of that, the redshift means the incoming light literally holds less energy and less momentum by the time it finally catches up to the sail.
That is wild. It creates this severe power drain effect.
It's like you're outrunning your own fuel supply.
Okay, let's use a visual here. Let's assume the lunar laser array is firing in the high-energy ultraviolet spectrum, right?
Okay, good example. UV lasers.
When the sail is just starting out, moving slowly, it receives the full impact of those high-energy UV photons.
Full power, maximum thrust.
But as the sail crosses 0.3c, the Lorentz factor begins to aggressively stretch that light. So from the perspective of the atoms on the sail, the incoming laser isn't ultraviolet anymore.
No, it has downshifted. It's probably in the visible spectrum now. Maybe yellow or even red light.
And as it approaches half the speed of light, 0.5c,
the light downshifts even further into the infrared, or maybe even microwave bands.
So the faster the sail goes, the weaker the push from each individual photon becomes.
Which means your thrust curve flattens out dramatically.
Which means the engineers back on Earth have to continuously pump exponentially more gigawatts into the laser array just to maintain even a tiny fraction of the original acceleration.
Exactly. Or, and this is more likely, they actually have to design the laser array to actively tune its emission frequency over time.
Wait, like changing the color of the laser as the ship flies away?
Exactly. Starting with something extreme, like X-rays, so that as the sail reaches relativistic speeds and runs away from the beam, the light downshifts into a wavelength that the sail's material is actually optimized to reflect.
That's incredibly complicated. You are just constantly fighting the fact that your propellant is basically losing its punch.
You are, but as brutal as this Doppler redshift is on your energy budget, it is still just an inefficiency.
Right, it just slows down the rate of acceleration.
Exactly. The really crucial revelation in Shen and Lee's research is what happens when you push the sail to exactly 75% of the speed of light.
The 0.75c wall.
The 0.75c wall. Because right at that specific velocity, the physics of that third force we discussed, the messy, inefficient, diffuse scattering it, stops being just a simple energy loss.
And it actively mutates into a mechanical brake.
Yes. It becomes a drag force.
Okay, this is the phenomenon of relativistic light aberration. And I know this requires us to strictly separate our frames of reference to really get it.
Oh, we have to. It's the only way relativity makes any sense.
So let's return to the perspective of an astronaut riding on the sail. In their local frame of reference, nothing has changed, right? The diffuse scattering behaves exactly as we described earlier.
Exactly. To the astronaut, the laser hits the sail, the atoms absorb some photons, and they randomly re-emit them in a standard, uniform distribution across the entire back half of the sail.
So, to the astronaut, looking out the back window, the light is still leaving the rear of the ship, just scattering harmlessly into the void behind them.
It looks perfectly normal. But the reality of special relativity means the universe simply doesn't agree with the astronaut's perspective.
Right. We have to look at the geometry of that scattered light from the stationary frame of reference.
From Earth or from the laser array, the origin point of the coordinate system.
Because the sail is moving forward at 0.75c, the Lorentz transformation suddenly applies to the angle of the emitted light.
Yes. It is commonly referred to in astrophysics as the headlight effect.
The headlight effect. Okay, how does that work?
Well, when an object emits radiation isotropically, meaning equally in all directions in its own rest frame.
Like our sail doing the diffuse scattering.
Exactly. When it does that, an observer in a stationary frame will actually see that radiation beamed forward, tightly concentrated in the direction of the object's motion.
Wow.
And the faster the object moves, the narrower and more forward-directed that cone of radiation becomes.
So this applies directly to the diffusely scattered light on our sail.
It does. As the sail accelerates, the stationary observer back on Earth sees those randomly scattered rearward photons, essentially folding forward.
Folding forward.
Their angles of emission are literally swept into the direction of travel by the relativistic speeds.
Okay, so if I'm tracking the math here, even though the light is physically emitted from the back surface of the sail, the extreme forward velocity of the sail itself just completely overpowers the rearward trajectory of those photons.
Yes.
To the stationary universe, that light is no longer moving backward at all. It is hurtling forward ahead of the sail.
That's exactly what's happening. And because momentum absolutely must be conserved in all reference frames.
We have a catastrophic inversion of Newton's third law.
Exactly. Think about it.
Yeah.
To generate forward thrust, you must expel energy or mass opposite to your direction of travel.
Right, you throw something backward to go forward.
Yes. When the diffuse photons were scattering backward at lower speeds, they provided a tiny, albeit inefficient, net forward push. But as the sail reaches 0.75 c, the relativistic aberration becomes so incredibly extreme that the net momentum vector of the diffusely scattered light actually points forward in the stationary frame.
Meaning the sail is now effectively expelling photon momentum in its direction of travel.
Yes, and the reaction force to a forward emission
is a backward push.
Exactly. Diffuse scattering flips from a weak thruster into an active drag parachute.
That is just, it's mind-blowing. The universe is taking the gigawatts of energy that we're actively pumping into the sail from Earth, and it's using the sail's own microscopic imperfections to break the spacecraft.
It is an incredible, highly counterintuitive speed trap.
It really is. The faster you try to push past 0.75 c, the more forcefully your own scattered light shoves you backward.
Right.
Which, I mean, that raises the immediate question of whether this represents a hard physical limit. Like, does the sail hit this relativistic wall and just completely stop accelerating entirely?
And that is a vital distinction to make. Based on Shen and Lai's paper, it does not represent a hard stop.
It doesn't.
No. The net force on the sail remains mathematically positive.
Okay, so it keeps moving faster.
Yes. The forward thrust generated by the incident light, plus whatever remaining specular reflection you have, even heavily weakened by the Doppler redshift we talked about earlier, all of that still manages to just barely overpower the backward drag generated by the aberrated diffuse scattering.
So the sail will technically continue to accelerate past 0.75 c.
It will. However, the energy economics become completely untenable.
Right, because you're fighting yourself.
Exactly. You are pouring staggering, mind-boggling amounts of energy into the propulsion system,
Yeah.
and the vast majority of it is being consumed simply to fight the drag force created by your own messy photon emissions.
So the cost-to-benefit ratio of pushing a spacecraft from, say, 0.75 c to 0.8 c, that might require more energy than pushing it all the way from 0 to 0.75 c in the first place.
Easily could. It's a wall of diminishing returns.
But we also have to acknowledge the boundaries of the theoretical physics models being used here, right? Because Shen and Lai are relying on the concept of an idealized mirror interacting with pure radiation.
Right, they map the absolute theoretical limits of photon momentum transfer.
But to isolate those specific relativistic variables, they necessarily had to strip away the environmental reality of the actual interstellar medium.
Which is a huge factor, because the vacuum of space isn't actually empty.
Right. What's out there?
Well, it contains trace amounts of interstellar gas, primarily hydrogen and helium, along with, microscopic dust grains scattered about.
Now, when a spacecraft is moving at slow speeds, like our Voyager probes, the interstellar medium is basically a non-issue.
Completely negligible. But kinetic energy scales with the square of velocity. And at relativistic speeds, you have to factor in the Lorentz multiplier on top of that.
So it gets bad.
Very bad.
Yep.
Traveling at 75% of the speed of light, a collision with a single stationary hydrogen atom is essentially a high-energy particle physics event. You are essentially flying a giant particle accelerator directly into a cloud of ambient gas.
So the physical drag from just slamming into that gas would be immense on its own.
Immense. And beyond just the kinetic drag, you have the thermal nightmare of Bremsstrahlung radiation.
Bremsstrahlung radiation, what is that in this context?
It's breaking radiation. Those relativistic collisions with the hydrogen atoms are going to generate a massive bow shock of X-rays and gamma rays.
Meaning you are dumping unimaginable amounts of heat directly into the sail itself.
Exactly. The theoretical paper treats the sail as an infinitely resilient geometric plane, which is necessary for the math. But in reality, you have a multi-terawatt laser pumping immense heat into the back of the sail and relativistic hydrogen atoms blasting gamma ray heat into the front.
So just sustaining the physical integrity of this ultra-thin, highly reflective material under those thermal loads.
Without it instantly flashing into plasma.
Yeah, without it vaporizing. That is an engineering hurdle that honestly dwarfs the math of relativistic light aberration.
It really does. The material science required to actually survive the journey dictates that we cannot rely on simple reflective metals.
like mylar or aluminum foils, right?
Yeah.
Which were the staples of all the early solar sail concepts.
Right, those would melt in a microsecond. The solutions being actively developed right now in aerospace engineering focus heavily on advanced metamaterials and highly tuned photonic crystals.
Okay, we really need to unpack the mechanics of metamaterials here, because this is where the theoretical physics actually translates into tangible hardware.
It's the practical application of all this weird relativistic math.
Right. And we aren't talking about discovering a new element on the periodic table.
No, a metamaterial derives its unique properties not from its base chemistry, but from its physical, microscopic structure.
So what does that look like?
We're talking about engineering a physical lattice of nanoscale resonators. These are dielectric structures that are physically smaller than the wavelength of the light hitting them.
Smaller than the wavelength of light. That's incredibly tiny.
It is. You are essentially constructing an artificial refractive index.
Okay, explain that.
Well, when an electromagnetic wave, like our laser, interacts with a naturally occurring material, the response is dictated completely by the atomic properties of that specific material. You get what you get.
Right.
But with a metamaterial, you design a physical grid. Perhaps using, say, silicon or titanium dioxide nanoparticles, arranged in incredibly precise geometric patterns.
So it's like a maze for light.
Kind of. When the incoming laser light enters this sub-wavelength lattice, the structure forces the electromagnetic field to oscillate in highly specific engineered ways.
So you can control it.
You can trap the light, you can manipulate its phase, and you can dictate exactly how it exits the material.
So instead of a flat mirror where a photon hits a stray atom and just scatters randomly, which causes our whole diffuse drag problem in the first place, the photon enters this specifically engineered maze.
Exactly. The metamaterial forces the photon to navigate the lattice and exit perfectly in the opposite direction.
Meaning you are aggressively engineering the diffuse scattering out of existence.
That's the goal. You force almost 100% of the interaction into perfect specular reflection.
And if you remove the diffuse scattering entirely, you drastically reduce that relativistic drag penalty at 0.75 C.
Yes, you neutralize the aberration break. But you have to remember, you tune the resonant frequency of that photonic crystal to the exact wavelength of your driving laser.
Oh, and we have the Doppler shift to worry about.
Exactly. You have to account for the Doppler shift we discussed earlier.
Right, because the laser color is changing from the sail's perspective.
Yes. So the sail might actually require a gradient structure.
A gradient structure.
Meaning different layers of the metamaterial tuned to different frequencies stacked on top of each other.
Oh, wow. So as the sail accelerates and the incoming laser light redshifts down,
the light penetrates deeper into the sail. It passes through the layers tuned for UV, and it hits the specific lattice layer buried deeper inside that is designed to reflect that lower frequency, visible or infrared light perfectly.
that is just a staggering level of passive engineering.
It really is. It has to do all of this automatically.
But the application of metamaterials goes beyond just mitigating the aberration drag, doesn't it?
Oh, absolutely.
Because there is this deeply elegant concept in aerospace design where you try to take the hostile physics of the environment and actually use them to your advantage.
Right, turning a bug into a feature.
Yeah. And maintaining the spatial alignment of the sail is arguably, the most terrifying point of failure for an interstellar mission.
It's a massive challenge. You have a laser beam traveling over vast astronomical distances.
Trillions of miles.
And the beam will naturally diverge, right? It widens as it travels. But the core of the beam remains incredibly intense.
So the sail has to stay perfectly centered on the peak intensity of that beam for years.
Yes. And if the sail drifts even slightly off axis,
the uneven radiation pressure will induce a torque.
The sail will begin to spin, it'll tilt, and ultimately it'll just fly off into the dark, completely missing the target star.
And you can't steer it. Active stabilization is incredibly difficult because you cannot afford the mass penalty of carrying chemical thrusters.
Or gyroscopes, or heavy onboard flight computers to steer the sail.
Because every gram counts. The entire mass budget is dedicated purely to the payload and the crystal lattice.
Exactly. The stabilization must be entirely passive. It has to be built directly into the optical properties of the sail itself.
And this is where engineers can leverage the very relativistic phenomena that Shen and Lai detailed, right?
Yes. By carefully designing the asymmetry of the metamaterial, you can actually create restorative optical forces.
Okay, I picture this operating similarly to the aerodynamics of a badminton shuttlecock.
That's a perfect analogy.
Because the shuttlecock doesn't need active steering, right?
Right.
Its physical shape ensures that no matter how chaotic its flight path becomes, the asymmetric aerodynamic drag forces its heavy nose to point directly into the direction of motion.
It naturally rights itself.
Exactly. So we can apply that exact same principle, but map it onto the geometry of space-time and photon scattering instead of air resistance.
Yes. So imagine the sail begins to tilt relative to the incoming laser beam.
It's drifting off course.
Right. When that happens, the angle of incidence changes. The photons are now striking the subwavelength structures of the metamaterial from a slightly skewed angle.
Okay.
You engineer the lattice so that when this specific off-axis angle occurs, the material intentionally breaks its perfect specular reflection on that specific side.
Oh, it purposefully induces a controlled amount of diffuse scattering.
Exactly, just on the side that's tilted.
And because the sail is moving at relativistic speeds, we know exactly what happens to that diffuse scattering.
The headlight effect takes over.
The relativistic aberration turns that localized scattering into a localized drag force.
Exactly. You are utilizing the aberration-induced drag as an asymmetrical brake.
That's brilliant.
The side of the sail that is tilting out of the beam experiences a sudden spike in relativistic drag.
Which pulls that side backward.
Yes. It naturally generates a restorative torque that pulls the sail back into perfect alignment with the beam.
And then once it is aligned,
the angle of incidence returns to zero, the material resumes perfect specular reflection, the drag disappears, and the acceleration continues.
Wow. It is a completely self-correcting optical mechanism that operates entirely through the interplay of nanoscale engineering and the extreme laws of special relativity.
No moving parts.
No moving parts, no sensors, just the raw geometry of light reacting to the curvature of space and the speed of the vessel. We are literally taking the universe's speed limit penalty and turning it into the steering wheel.
It's incredibly elegant.
Yeah.
And it perfectly illustrates the necessary evolution of our approach to interstellar travel.
We can't just force our way through.
No, we cannot brute force our way to another star system. The environment at a significant fraction of light speed is far too hostile, and the energy requirements are far too unforgiving.
We have to play by the universe's rules.
We have to map out the highly nonlinear dynamics of relativistic flight. Understanding how variables like the Doppler shift and relativistic aberration compound upon one another, and then weave our engineering directly into those constraints.
This whole journey from the macro to the quantum scale really recontextualizes the entire challenge for me.
It's a completely different paradigm.
Yeah. I mean, we started with the sheer mass problem of the rocket equation, right?
Yeah.
The realization that we have to just abandon chemical fire and rely on the massless momentum of photons.
And then we explored the mechanics of that thrust.
The incident strike, the perfect bounce of specular reflection, and the messy reality of diffuse scattering.
We examined how velocity itself begins to degrade our power supply through the Doppler redshift, forcing the laser to push against a rapidly fading target.
A target that's literally changing colors as it runs away.
Yeah.
And then we hit the aberration wall at 0.75 C, where the stationary geometry of the universe folds our own scattered light forward.
Creating an inescapable relativistic headwind out of our own propulsion energy.
Right. And then we moved from the theoretical whiteboard calculations of Shen and Liu right into the physical laboratories, developing the actual photonic crystals and subwavelength metamaterials required to survive and, even exploit that headwind.
The depth of understanding required to even conceptualize a functional light sail is just profound.
It's staggering.
It demonstrates that crossing the interstellar void is less an issue of generating enough raw power and more an exercise in extreme physical choreography.
Extreme physical choreography. I like that.
Because we have to perfectly balance the thermal load, the relativistic collisions, and the quantum mechanics of photon absorption across distances measured in light years.
Which leaves a really fascinating philosophical thread to pull on as we look at the monumental difficulty of this whole endeavor.
Oh.
Yeah, because when you map out the compounding obstacles, the tyranny of the rocket equation, the punishing redshift, the relativistic aberration that literally uses our own energy to push back against us.
That's daunting.
It feels almost intentional.
Intentional? Like how?
It forces you to wonder if the actual architecture of space-time, with its inescapable aerodynamic limits and mass penalties, acts as a sort of natural quarantine protocol.
Oh, I see.
Like it's inherently designed to keep biological species localized within their origin systems.
The universe doesn't want us leaving the nest.
Exactly. Or, on a more optimistic note, whether these relativistic speed traps are simply the ultimate, unfiltered test of a civilization's maturity.
A technological rite of passage.
Right. A final engineering gauntlet that forces a species to fully master the quantum and relativistic domains before they are actually permitted to sail across the dark.
That's a beautiful way to frame it.
It is an extraordinary puzzle.
Yeah.
And the fact that we are currently designing the metamaterials to solve it right now in labs on Earth means we might just see a piece of human engineering riding that beam of light in our own lifetime.